We've looked at multiplying points in our polar points in the complex plane. We looked at dividing those. Let's look at how we can go ahead and look at some power types of ideas. So let's say I have some point z, which we know is defined as its modulus times cosine theta plus I sine theta. Let's multiply it by itself one time. So z, I'm going to try to do this in different pins here. So z times another z gives me a z squared. So I take the first z, which is r times cosine theta plus I sine theta. Multiply that by its second z, which is r times cosine theta plus I sine theta. We remembered how to multiply. We multiply its moduluses. So I would then get r squared, r times r squared. Then I take cosine, add their arguments. Theta plus theta gives me 2 theta. Theta plus theta gives me 2 theta for the sine. And so there's r squared. Or sorry, not r squared. Yeah, so z squared equals r squared times cosine 2 theta plus I sine 2 theta. Let's find the next one out. Let's take z squared, multiply it by z again, so basically z cubed. So I have r squared times cosine of 2 theta plus I sine of 2 theta. Multiply it by another r, or another point z, which was r times cosine theta plus I sine theta. Again, multiply it like we've learned before. R squared times r produces an r cubed. And then add the arguments. 2 theta plus 1 theta gives me 3 theta. 2 theta plus 1 theta gives me 3 theta again. And so z cubed equals r cubed cosine 3 theta plus I sine theta. You want to do one more? Sure, why not? Let's do one more. So let's take z cubed times z again to essentially give me z to the 4th. So that becomes r cubed cosine 3 theta plus I sine 3 theta. Multiply it by another z, r times cosine theta plus I sine theta. Multiply the moduluses, or multiply it with moduli, moduluses, modulu. So z to the 4th equals r to the 4th cosine 4 theta plus I sine 4 theta. Tracking along, seeing a pattern there? Yeah, we've discovered a pattern that basically looks like that for every index that I raise z to, I'm raising its modulus to that index, and then I'm multiplying the argument by that number as well, by the index. And so what we have is we have I cannot do my French, DeMoivre's theorem, which says that z to the nth equals r to the nth times cosine n times theta plus I sine n times theta. So given that, we can take any complex number written in the polar form, in the polar coordinates, and use that to raise it to the whatever powers we need to raise it to. So for example, the example that we're going to look at. I know I have no room here anymore. 2 cosine 20 degrees plus I sine 20 degrees. I want to raise that whole thing to the 6th power. And so we can multiply itself times itself times itself times itself times itself 6 times. Or we can understand and use this pattern that we have, DeMoivre's theorem, that helps me get it to it right away. So 2 to the 6th power is 64 cosine 20 degrees, multiply that down, that's 6 times 20 degrees. So I have cosine of 6 times 20 degrees, gives me 120 degrees, plus I sine 20 degrees times 6, 120 degrees. Remember, I'm not taking 20 to the 6th power. Here we're adding the arguments. Remember, you add the argument, you multiply the the modulus, you add the argument. So I'm adding 20 degrees times itself, or adding it to itself 6 times. So that's why I have 120 degrees. 64 cosine of 120 degrees. That's over in the second quadrant. Cosines are negative in the second quadrant. So that's a negative 1/2. Plus I, the sine of 120 degrees. Sine of 120 degrees is positive in the second quadrant. So that was a √3 over a 2. There I can multiply the 64 on out. So 64 times a negative 1/2 gives me a negative 32 plus 32 I √3. So there I took that point that we found in the complex plane written in polar coordinates, was able to multiply itself 6 times or take it to the 6th power, and using DeMoivre's theorem, I was able to go ahead and understand that I'm going to take its modulus and raise it to itself n times, which is 6, and then add its arguments to itself 6 times, and I was able to reduce it down to minus 32 plus 32I √3.